yeah, first I want to thank the organizer for the invitation. I enjoyed this series of seminar a lot, and it's great pleasure to give a presentation here. So yeah, I will talk about part of this mostly joint work with Jiayin Pan. He is going to give second talk, and some part with Day, Honda, and Pan. So I will think this in three parts. First, it's about Ricci limit space. Then some results. Then second part focus on non-compact manifold with non-negative Ricci curvature. Okay, so then a very little about constructions, which maybe I think second talk maybe talk more about it. Okay, and also the second part, the Pan will talk a lot more. So about Ricci limit space, I think so we don't need to define the Gromov-Hausdorff distance here. The starting point is so-called the Gromov's pre-compactness theorem. Namely, if you have any sequence of manifold with Ricci lower bound and dimension, we usually always fixed, okay, in this case, the fixed dimension, then you can always have a subsequence converge in the Gromov-Hausdorff limit. And so those limit we all refer to as now as Ricci limit space because they're coming from the space with Ricci lower bound. Okay, so, studying the Ricci limit space is really very important to study manifold with Ricci curvature lower bound. They really go together in this case. So for Ricci limit space, we usually divide it into two cases. One is so-called non-collapsing, namely if the sequence in addition, the volume of the unit ball is uniformly bounded from below, or when it's going to zero, that's called collapsing. Okay, so they might have two different sound structures are maybe different, but in general, they are all Ricci limit spaces. Okay. All right, so then we would like to study this in order to, okay, I'll just make one connection because nowadays this all refer to so-called RCD space. So I will not define the RCD space, just to say that those are the space such that in synthetic sense, the Ricci curvature has bounded from below. And dimension, so instead of definite dimensions, the dimension is only bounded above by n in this. And R is referred to Riemannian case. Okay, so for us, instead of going to definition, it's just convenient that the Ricci limit space we did in the first page are indeed RCD space. So the curvature will be bounded from below by negative n minus 1, that's we said, and dimension above by n. So sometimes I'll just refer to the then as RCD space. So this is basically this is a subset. Yeah, Ricci limit space a subset of RCD space. Okay. All right. So there's lots of things I talk about can be extended to RCD space. So this RCD limit space usually are far away from manifold. So to study the regularity or stuff, it's natural to define what is a tangent space. So tangent space is a limit also because I can blow up this space. This limit will still limit always, a subsequence always has a limit. Basically, you let R go into infinite. So it's blowing up the point. And this limit, a subsequence always exists. The limit may not be unique. All those limits together are referred to the tangent cone at the point. Okay. So if the point are nice, then namely the tangent cone, it's like Euclidean space. That's like a manifold. Then we call the point regular. So it's nice. So usually all the and K refer to the K here. So all those point is called RK, so K regular. Otherwise, it's a singular point. So in the manifold case, of course, all of them are regular point. Okay, so that's a way to distinguish those points. So regular means nice and infinitesimally Euclidean. So here are some properties about Ricci limit and or RCD space. I'll just focus on Ricci limit space. Instead of the geometry, I start with topology because it's not as many. So the topology in general, it could be really bad. Even for non-collapsing, these usually should be better. Mangu give example that, at some point, the local topology could be infinite. For example, second Betti number may be infinite in an arbitrarily small neighborhood. And then very recently, neighbor Hub one, they give example for collapsed case, then this could happen at every point. Every point in arbitrary neighborhood, the second Betti number could be infinite. Okay, so it could be really, really bad. And compared to, usually if you have the sequence that have sectional curvature law bound, those limits are usually called Alexander space. And we know before, those spaces are always locally contractible. So it's much, much better. So those are, not so good. So then what are the positive results? One of the first positive results, I think it's back 20 years ago, is joined with Salmani and I showed that Ricci limit space does have at least a universal cover. So the universal cover here, it just means cover of all cover. We don't at this time assume it's simply connected. I mean, even though sometimes people define universal cover as simply connected. So that's not the, so we know that if it's a simply connected universal cover, then it's a semi-locally simply connected. So that's in the, later on, Mandino and I extend to RCD space. So it's along the same line, just streamline the proof. Then that's usually the result. Then recently, we improved to first also joined with Penn. This is we first proved for non-collapsed Ricci limit space. It is really actually not only semi-locally as locally simply connected. It's essentially locally simply connected. So in particular, the universal cover is it's simply connected. Okay, so this we just proved directly without using the previous result. Later on, in several works, finally, Guofang Wei, he proved that this is true for any RCD space. Actually, it's semi-locally simply connected. So this solves the problem along the line. This one he used actually previous result essentially. So any questions? This is a topological part, which I'm not planning to give any proof. Now let's get to the regularity part. The or maybe geometry. This a lot more work is in this direction. So I will actually only list a few which will be used in the later talks. So one of them is due to Cheeger-Colding and Colding neighbor. From their work, you can say for any Ricci limit space, there is unique integer k, which is between 0 and m. First is that for this Ricci limit space, one can always define a renormalized limit measure. Okay, I didn't define it, but it's some kind of limit measure, such that the regular set, we said it has 4 measures. So that means singular set has measure 0. So essentially that with respect to this renormalized limit measure, the space are quite nice, infinitesimally, means everywhere is really nice. And you can, from this definition, you can say the Hausdorff dimension of regular set, Rk is just equal to K, okay? So now we can associate a Ricci limit space, a dimension. It's usually called a rectified dimension because this K is integer, it's unique. So this is for general Ricci limit space. Now, for the non-collapsing case, if it's non-collapsing, so that's additional assumption, then we can say more. Then in that case, the rectified dimension and the Hausdorff dimension are both equal to m, the maximum possible, okay? And not only that, the singular set has co-dimension 2, so it's less than m minus 2. So in the non-collapsing case, so this the rectified dimension and Hausdorff dimension is always the same. So in their paper, they ask, is this generally true? Namely, for collapsing case, is the dimension also equal, rectified and Hausdorff? This is equivalent to saying that the Hausdorff dimension of singular set is less than the regular set. This may be a little, which somewhat conceivable because, right, with respect to the renormalized limit measure, the regular set has 4 measures. So maybe we say singular set is also smaller than the regular set in terms of Hausdorff dimension. So recently, Peng and I gave a negative answer to this question. Namely, we can show that there you can just take actual topology. It's just Rn, very simple, with that has positive Ricci curvature, and the asymptotic cone, which is just maybe cone at infinite. You scale back. Okay, so it's also a Ricci limit space, a very special Ricci limit space. For this Ricci limit space, the regular set is R2, so it's 2-dimensional, but the singular set is 1 over alpha, and we can do it for any alpha as long as m is big. So if you choose alpha is big, then the singular set dimension is bigger than the regular set. So in general, so this means that also the limit measure and Hausdorff measure they're really not, absolutely continuous. So they behave very, very differently from this example. Okay. So any questions? All right. Yeah. Going a bit quick. Okay, so that's the part I first talk about Ricci limit space. Next, well, actually, sorry, not done yet. I have some applications. Okay, so that's when we do it first, and later on we studied. This is joined with Day Honda. In addition, we studied more about these examples. We can have actually very simple description about this metric. You can think, right, this is just a half plane, and the metric is blow up. It's something like this. This is blowing up, and the measure is degenerate. So m is bigger than alpha. This is degenerate. And this is blowing up. Okay, so this is everything is a very explicit, concrete description about these examples in the. Okay, so from this construction, okay, so then we can much more clearly you can talk about the so therefore, because of the degenerate measure, even though this looks very, very negative, because the measure is a very degenerate, this function, the convex, is still RCD OM. Okay, so again, it's just a language, namely, it's still Ricci limit space with non-negative Ricci curvature. And it's cat 0. So it's that's just a metric. We can see it's very, very negative. And from this, you can see also quickly that it has dilation. If you define the map by this, different power, then the distance just dilate by lambda. So this is like a, for the cone has a special structure. So this space has dilation. Once you have this dilation, you can see actually the distance between 0 and 0R. So those are the singular set. I should draw this space. It's like this. It's a half plane. These are the singular set, and these are the regular set. So this is a singular set. Okay, so the distance along the singular set, it's not, so this is 0, 0, and 0V. So the distance, it's like a V to the some power. From here, you can see quickly the Hausdorff dimension is 1 plus alpha. Okay, so precisely. So the motivation when we study this more, we were trying to study so-called, Weyl law before. So another surprising relation we found from this metric is that these are so-called the Gaussian plane. So this is studied in sublimian geometry a lot, actually. So this is quite surprising because before sublimian geometry and RCD, really they disjoint. So there they study the whole plane. The whole plane is not RCD. So there's lots of result about sublimian cannot be even CD. So this gives a new connection between sublimian geometry and Ricci limit space. Okay. So the reason we were doing is we try to study so-called Weyl law. This is a count how many eigenvalues of the Laplacian less than some number, just like you do with a prime number, is how many numbers are less than n, which are prime, so these eigenvalues. So Weyl law look at asymptotics when lambda going to infinite, what it look like. So in the earlier for manifold or early result, usually this beta is always integer. So from here, this example we can take, it could happen that beta could be any number, and Weyl law, it captures the dimension is from the singular dimension. So this is very different from early. This is first example also has this feature. So beta could be, as we said, any number could work. Moreover, we can also have another. Okay, so this we need to modify the example. This example a compact one, so it's a RCD negative one here, and this one is instead of power, it has a log of lambda. Okay, so this is I don't know. We basically see it more like a space, more like a fractal, the first order. Again, this is captured by the singular set instead of the regular set in this case. Okay. All right, so this really gives new features, I think, for Ricci limit space. Okay, I think that's it. Any questions? Okay, so this is...
I have a question. I have a quick question. The previous slide, you said that it was cat 0 and RCD non-negative. So
yes.
Would you say it's kind of Einstein in some weak sense?
Not real. Well, in RCD, I need to get the measure, the weighted measure. And when it's 0, then there's no measure talking about. Yeah, I mentioned this because I think a couple of which they have some conjectures about cat 0 and RCD, and that we also give a counterexample to their.
Oh, okay.
Thanks. Okay.
Thank you.
Okay, so now let me start on the second part. It's about non-compact manifold with Ricci curvature bond. For non-compact manifold, a very useful function is so-called Busemann function. This is just a distance function. So namely, if you have an array, then you take the x, and then you just take the distance to the array, and bigger, but that's infinite. So we renormalize it by t here, p minus. So it's a renormalized. It's in some sense distance from infinite, but renormalized. This is a Busemann function associated to array, and here it's we will focus on Busemann function associated to a point. That's by taking this Busemann function, then take supremo among all the rays from the point. Okay, so this, and that's the one we're going to. Most of the time, people refer to the rays, and here I will always refer to the point, the Busemann function. As you said, this function studied a lot. It's really, really useful. So in Cheeger-Colding, when they approved the Soul theorem, I mean, they studied the Busemann function. One of the key steps is show that this function is convex. Okay, once you're convex, then it follows that it's a proper. In this case, even more, proper just means that the compact, the inverse image of compact set is compact. Here, even more, you can say this image is compact for negative because it's a convex, so it cannot really go to negative infinite. So this is compact. So that's for sectional curvature greater or equal to 0. Okay. Now for Ricci curvature greater or equal to 0, usually instead of convex, you can think here is convex is a Hessian, right? We have the Hessian of the Busemann is greater or equal to 0. Now in here we have the Laplacian subharmonic in weak sense greater or equal to 0. So we take in trace very natural. This also plays very important role in the splitting theorem, in their proof of splitting theorem. So Busemann function is now from this you can ask the question. Actually, after this work, I think Pan Jiayin was giving a talk at CUNY, and want to thank Christina mentioned this problem to us. Kind of forgot. So this was Jeff said this is open since the splitting theorem. We can ask now: is the Busemann function actually also proper for non-negative Ricci curvature? Okay. So there's several positive results already. So that's, since the 70s already open. There's some positive results. One of them is by Zhongmin Xin, under the assumption that the volume growth is Euclidean. So in some sense, it's a maximal volume growth. So this is a maximal case. And another case is by Cristina Salmoni. She did it when linear volume growth. That is a minimal volume growth case. In these cases, the Busemann function are both proper. Okay, they proved. So there is no, I think, really other works. It's also, more than 20 years ago. As they said, after Christina asked a question, we look at examples. We can show that from this example, she also gave a negative answer to the, namely for dimension big or equal to 4, we can find that the Busemann function is not proper, okay, with positive Ricci curvature. I think dimension 3 is still open, surprising. I thought should be already known, but don't know the result. Okay, so any questions so far? Going a bit quick. Well, okay, so from this you can ask, is there so when it will be true? So then we look at the Shin and the Salmoni's result. because this, in their case, either it's a linear volume growth or Euclidean volume growth. And then if you look at the asymptotic cone, it's all kind of nice. It's a polar. It's a relatively, actually, it's even a metric cone. So you can ask, what if you assume all the asymptotic cones are nice, namely like a polar? Then does that imply the Busemann function is proper, right? Because in the positive direction, that's the case in the positive direction. So you can ask, is this will be true? Then we also answer this in negative, namely, you can, okay, in this case, it's not dimension 4, but dimension a little bit higher. We can have asymptotic cone. It's actually just a half plane, so it's definitely polar. It's a metric cone, but the Busemann function is also not proper. Yeah. And so this does not. So yeah, I think all these lead to lots of questions. Maybe Jiaying will mention later, like, yeah, when will it, proper, it's related to what property maybe. Questions? Okay. So how do we prove it? The proof of both counterexamples kind of related. It go back to the Nabanan's example in the 80s. Okay, so he constructed a double warp productless metric on the Euclidean space times S1. Okay.
Guofang, I have a question. Yeah. Maybe it's elementary. And you mentioned that the properness of the Busemann function is important to get the splitting theorem.
Mm-hmm.
And does this mean that
the subharmonic, not the proper part. It's
okay, good. Yeah, okay, no, sorry. Yeah, I was confused. Yeah. Mm-hmm.
Okay. Yeah, the fact that it's subharmonic was a key part. Yeah. Right. Okay, so the example is so this is RK, so Euclidean, then you warp with S1. Okay, so you double the functions, double warp F and H in this case. So we're going to specify this function later, but intuitively this picture is that H is decreasing, and F is increasing in this way. So why this example? This is the first example that Ricci curvature is strictly positive, but fundamental group is infinite, right? Okay, so of course this for open manifold, this cannot be true for sectional curvature, of course. So positive sectional curvature, positive open manifold is diffeomorphic to Rn, Euclidean space. So here, maybe in this picture, I'm not sure. Actually, we got it from Salmani Shen's paper. So this is maybe the H, the length. It's getting smaller and smaller, this H. And here is F. It's getting bigger and bigger, and you rotate it. So if you look at just this 0 to infinite and S1, then you just looks like a surface, right? Then you rotate with a sphere getting bigger and bigger. So I say the F is, okay, I'll later on more specify. So F is going to infinite in certain rate, and H is decreasing. Actually, could be 0 or could be some constant. Okay, so that's the once you compute it, that will make a positive Ricci curvature. And later on in my thesis, I extended this construction instead of S1. Actually, I should say Boulard-Bourgeois can replace the S1 by any manifold with non-negative Ricci curvature. So here I take, instead of that, it takes a new manifold. New manifold does not have a metric with non-negative Ricci curvature, right? So but the wall product together, it also has Ricci positive. So this is the first example showing that the fundamental group of manifold with positive Ricci curvature could be unimportant. Does not. Okay. So here is infinite, and this is nilpotent in this example. Okay, so now just maybe indicate how do we construct the nonproper, show the Busemann function. Actually, basically, we just take this Nabonance construction. Now we take the universal cover of this. So universal cover will be just a Euclidean space, right? S1 will be just a R, okay? Take the universal cover, and we take, so we can show that as long as H goes to 0, then the Busemann function of the universal cover is always not proper. So as long as. And the other one, now if we go to 0, relatively slow, namely logarithmic decay, then we can show that the asymptotic home actually is polar. But, as long as go to 0, it's not proper. So therefore, the Busemann function is still not proper. Okay. Okay, so more, more maybe precise. So that's a big idea, in more detail. How do we do it precisely? We choose several steps. So in order to do whether do Busemann function, whether proper, because we look at the Busemann function at a point, so we need to look at all the rays starting the point. First, we have to find what are all the geodesics starting at that point, right? Okay. So this is in the universal cover, which is very related to the space in the bottom. So in how to do this, first step, say 1. First step is you find all the rays. Okay, sorry. First step is find all the geodesic in the bottom. Okay, so this is 1. Then from here, we can say that then all the rays in the universal cover here, it's always going to project to a radial ray, which are much, which are very simple in this case. Okay. So this may not be the rays. Okay, so these are really, a surface looks like this, and you can really study all the geodesic look like from, Clairaut's law and write explicitly. Then we can show that only this one, the radial, this will be the, in the top project, this will be the real ray. And finally, can show that this level set, the Busemann function of the level set, just 0, actually contains the entire orbit. The fundamental group is Z, so this cannot be compact. So that's not, basically inverse image of 0 is not compact. Okay, so that's indicate it's not proper. Yeah. Okay, so this is the argument. More actually somewhat elementary. So we find the examples. Okay. Now about the bigger the example, the singular set has a big Hausdorff dimension. Okay, we also write with the same example, but we choosing the warping function a little bit different. That's those we just from this my early construction with the nilpotent. So these are explicit and more concrete to work with it, because in the Nabonance construction, the function is not explicit. So as we said, the H is decreasing. I was decreasing this way, and F is increasing, and it's like this. So it's important that F, not increasing as much as the usual Euclidean case like R. So we intuitively you borrow some of the positive curvature from Euclidean to get the S1 in here. Okay, so once you have that, yeah, as we said, actually, in the earlier we estimate the distance as Pan-Weyl, but later on we can use a rescaling argument to show that. And this, because we look at the asymptoticon, it's just a rescaling, you can do the metric just precisely. So this is different from earlier. Earlier, I think, made R to the negative alpha, and this is square, so it's 4 negative 4 alpha. Okay. Once you have this metric, as we said, then you can define the scale function and define the distance and the regular set. Basically, it follows quickly that the singular set has Hausdorff dimension 1 plus 2 alpha in this case. So that's a very, very quick sketch of the idea. Okay, I think maybe.